We're going to talk about L'Hopital's rule today. The accepted spelling of this name has gone through like 4 revisions since I first learned it. So sometimes you'll see the apostrophe and sometimes you won't, and sometimes H will be capitalized and sometimes it won't, and sometimes there will be that mark above the O and sometimes there won't. But the important thing is that we know what it is and that we can use it. And L'Hopital's rule is a little weirdly placed. Because L'Hopital's rule is a limit rule. And of course, in the standard calculus curriculum, and of course we followed that, limits are sort of basically the first thing we do in calculus 1. And then we use them to define the integral, but we've really moved away. So it's at first blush a little weird that we're learning this rule now, but we're going to want it in the second half of this class, once we start talking about sequences and series. And before we introduce L'Hopital's rule, let's talk about determinate and indeterminate forms. 99 times out of 100, when you're using L'Hopital's rule, X is going to infinity, but I'll write C there. And again, in the vast majority of cases, the function we're looking at is written as the quotient of 2 functions. And let's look at, we have this rule, and of course I've not used it since the early days of calculus 1. But the limit of a quotient is ordinarily just the quotient of the limits. So, if you want the limit as x approaches 5 of 2x divided by x plus 1, it's, forgive my kind of sloppy notation, but it's the limit of 2x over the limit of x plus 1, and then 2x is continuous. We can just plug the 5 in, and x plus 1 is continuous. We can just plug the 5 in, so we can take the limit of this quotient. So sometimes a limit won't exist, right? Let's take the limit as x goes to infinity now of 5 divided by x plus 1. And let's try to use this quotient rule. Well, the limit of a constant is a constant. That's okay. Getting extremely sloppy with my notation. If x is going to infinity, infinity plus 1 is still infinity. And And you know, properly speaking, that limit on the denominator doesn't exist. When you say that a limit is infinite, you're saying that the limit doesn't exist, and then you're adding, but you know something about it. You know it's getting big. So properly speaking, we can't really use this quotient rule, except that we can, because when we have a limit of this form, where we have a finite number over infinity, that limit is 0. So even though the limit as x goes to infinity is indeterminate, it doesn't exist, we can still find the limit of this fraction. And this is an example of what I'll call a determinate form. I feel like you don't hear that phrase a lot. You hear a lot about indeterminate forms, but it makes sense that determinate would be the opposite of indeterminate. If you're taking the limit of a fraction, again, copying something from that previous frame, if you get a finite number over infinity, that limit is infinite, as we saw back here. If that situation is reversed, if we get an infinite number over a finite number, then the limit doesn't exist. And then if we get 0 over a non-zero finite number, well, this is actually a situation where you just use the limit rule. The top exists and the bottom exists, and 0 divided by any non-finite number is 0. Conversely, if the top is going to some non-zero number and the bottom is going to 0, the limit does not exist. And in both these situations where I say the limit does not exist, I mean, it's specifically, it doesn't exist because it's blowing up to infinity or blowing down to negative infinity. So these are called, or at least I'm calling them, determinate. And when I say determinate, what I mean is that we can determine the limit without doing any further work. So, you know, this might not be the easiest example because I don't know how many of us really remember the arctangent. But if you do remember that the arctangent looks like that it has a horizontal asymptote and is going to pi over 2. In the bottom, infinity squared is infinity. And we say, okay, we have a finite number over an infinite number. So this limit is 0. No muss, no fun. And if you look at this board, we've got zeros and we've got infinities, and there are only 2 combinations that aren't on this board. That's, well, what if the top and bottom are going to infinity, both? What if the top and bottom are going to 0, both? And these forms are called indeterminate. And you know that in indeterminate, we cannot determine the limit just from looking at that fraction. This is different from the previous 4 forms where we could. And I mean, it's, if we go to Desmos, so like x divided by e to the x. This is an indeterminate form as x goes to infinity. As x goes to infinity, this top is going to infinity, and this bottom is going to infinity. And if we just investigate the limit graphically, we can see what's going on. As x goes to infinity, this quotient appears to be going down to 0. Now, if we flipped those around, e to the x is still going to infinity, x is still going to infinity, so this is still infinity over infinity, but you see a different limiting behavior now. As x is going to infinity, this limit does not exist. This limit is just exploding up to infinity as well. Then if you look at 2 to the x over x plus 1, 2 times infinity is infinity. That's a very fuzzy statement, but I hope the intuition is clear. Infinity plus 1 is infinity, so this is still infinity over infinity. And as opposed to this, which is going to 0, and this, which is going to infinity, the limit doesn't exist. This is going to a different finite number. This is going to 2. So if we have infinity over infinity, we don't know what the limit is. We have to do some kind of further analysis. And the same is true for 0 over 0. And L'Hopital's rule is a rule for tackling these indeterminate limits. And the reason, well, there are a few reasons we're not talking about L'Hopital's rule until now. The first I've already given. We're going to want this for sequences and series, and that's really the first place we're going to use it. So covering it in Calculus 1 would be a bit silly because then we just have to review it in Calculus 2. The other reason, and I guess the main reason this doesn't get covered in chapter 2 when limits are covered, is that it uses the derivative. So even if we wanted to cover this in Calculus 1, it would have to be somewhere towards the end of Calculus 1. And you see, we start with the word if, and I've underlined it for emphasis. A mistake you see, well, students make sometimes, is using L'Hopital's rule when they should just be looking at the quotient and figuring the limit out using one of these rules. If this limit is indeterminate, if it has the form 0 over 0 or infinity over infinity, then the limit as x approaches c of this fraction is the limit as x approaches c of the derivative of the top divided by the derivative of the bottom. We are not using the quotient rule here. We are not taking the derivative of the fraction. We are taking these derivatives separately. And something you often see done by convention is that when people or textbooks use L'Hopital's rule, they'll put LH above the equal sign to indicate what they're doing. So L'Hopital's rule is not at all obvious. I'm sure that at some point in my career, I've seen a formal proof of this, but I really could not explain why this is true. It's something where I'm afraid going to just take on faith. But let's see L'Hopital's rule in action, and we may as well start with the examples we saw on Desmos. So this isn't going to be in the recording just yet. Let me hide these so that we can only see this. X over e to the x. So this is indeterminate. X is going to infinity. E to infinity is infinity. So this is indeterminate, and it's appropriate to use L'Hopital's rule. And L'Hopital's rule says, okay, take the derivative of the top. Well, the derivative of x is x, and take the derivative of the bottom. the derivative of e to the x is e to the x. And I said out loud that the derivative of x is x, which of course is not true, but I wrote on the board the correct statement that the derivative of x is 1. And now 1 just stays put. E to infinity is still infinity, but 1 over infinity is no longer indeterminate. One over infinity in the upper left corner, a finite number over infinity is 0. So according to L'Hopital's rule, this limit is equal to 0. And going back briefly to Desmos, that's precisely what we see on Desmos. As you know, this thing is going up for a while, but then as x goes to infinity, y is going to 0. You see here up to rounding error. Ooh. Contrast that, just expecting sparks to come flying out of this thing any day now. But I mean, anyway, contrast that to e to the x over x. This is indeterminate. E to the x goes to infinity as x goes to infinity. X goes to infinity as x goes to infinity, kind of a vacuous statement. And we see that the limit doesn't exist, that this thing is blowing up to infinity. Okay, so we see this limit. We do not just dive in and use L'Hopital's rule. I understand the temptation because this is the L'Hopital's rule section, but we cannot use L'Hopital's rule if we do not have an indeterminate form. I mean, we will get incorrect answers if we use this rule when the form is not indeterminate. So the first thing we always have to do is verify that this is a L'Hopital's rule problem. And it is. The top is going to infinity, the bottom is going to infinity. This is indeterminate. So the same derivatives as before. My notation is terrible, though. We shouldn't lose that limit. Okay, and now the top is going to infinity, the bottom is going to 1. This is no longer indeterminate. A infinite numerator, a finite denominator. This limit does not exist. It's blowing up to infinity. And for the last example, using L'Hopital's rule for this is maybe a little overkill. We teach students in algebra classes, even in, what the heck did I share? Let's try that again. We teach, high school. I hope that we're seeing Desmos in the recording. Things suddenly went very weird. I was saying, there we go, that this is something we teach college algebra students and even high school algebra students to do. So maybe hitting it with the tools of calculus is a little excessive, but 2x divided by x plus 1 as we go to infinity. So 2 times infinity is infinity. Infinity plus 1 is infinity. Again, an informal way of speaking, but this is indeterminate. This is infinity over infinity. So we can hit it with L'Hopital's rule. The derivative of 2x is 2. The derivative of x plus 1 is 1. 2 divided by 1 is 2. The limit of 2 is 2. So L'Hopital's rule says that this limit is 2, which hopefully this will go a little smoother. 100% didn't. That's what we see on Desmos. As x is going to infinity, we see y 1.96, y 1.97, y is going up to 2. So let's use L'Hopital's rule. We've done 3 semi-elementary examples. They were all the same indeterminate form. They were all infinity over infinity. Let's use L'Hopital's rule to take a very famous limit, famous in the extremely constrained setting of calculus classes. Let's take the limit as x goes to 0 of the sine of x divided by x. This is indeterminate. If we just try to use continuity, the sine of 0 is 0. And when we plug 0 into that denominator, of course, we get 0. So this is indeterminate of the form 0 divided by 0. And we can try hitting it with L'Hopital's rule. And the derivative of the sine is the cosine. And the derivative of x is 1. And I keep getting sloppy. We're still taking a limit here. And now we can try, everything here is continuous. If plugging 0 in doesn't give us a division by 0 error, then we can just do that. And the cosine of 0 is 1. So we don't get an error. We can just use continuity. This limit ought to be 1. And we talked about this briefly in Calculus 1, but I wouldn't expect people to really remember it. This limit is important because, I mean, what's it mean for a fraction to be 1? It means the top and the bottom are basically the same. So this is telling you that if x is close to 0, the sign and x are basically the same function. And it gets used to simplify complicated expressions. That is, if x is really close to 0 and we see the sign of x, well, the sign of x and x are basically the same, so we can just replace the sign with x. We'll talk more about that kind of approximation when we get further into this class. For now, it appears as if it was using the touch screen that caused that awkwardness earlier. So here's the sign of x divided by x. And we ask what happens as we approach 0. And of course, at 0 itself, this is not defined. We get a division by 0 error. But as we approach 0, these y's are getting closer and closer to 1. Let me see. Any questions so far? So you can use L'Hopital's rule. First of all, I mean, L'Hopital's rule is always true in the sense that if we have this indeterminate fraction, we always can use L'Hopital's rule. There's no guarantee that L'Hopital's rule will allow you to take a limit, though. It's possible that you use L'Hopital's rule and you can't take the new limit any more than you could take the old limit. But one thing you can sometimes do, and this is especially true when you've got polynomials, is use L'Hopital's rule more than once. So, for example, the limit as x approaches 0 of 1 minus the cosine of x divided by x plus x squared. So this is indeterminate. And in the homework, I think there are problems where you don't use L'Hopital's rule. The textbook author, just like me, wants to make sure you're doing this first step. But this is indeterminate. The cosine of 0 is 1, 0 plus 0 squared. This really is an indeterminate limit of the 0 over 0 form. So we can try L'Hopital's rule. Let's see, what's the derivative of the top? Positive sign. So the derivative of 1 is 0. That just goes away. The derivative of the cosine is the negative sign. we have two negatives. I keep getting sloppy. We're still taking a limit. So, okay, this was not what I thought it was going to be, but that's fine. We'll get the limit that we get. So as x approaches 0, what happens now? Well, the sign of 0 is 0. I thought I was going to have to use L'Hopital's rule twice in this problem, but it just ended up being a single use. And then we get a determinate form. 0 divided by 1 is 0. Let's take a look. So here's the function. At 0 itself, we have a division by 0 error, but we can see from the graph that as we approach 0, y approaches 0 as well, from the right and from the left. So this limit is 0. It is what L'Hopital's rule says it ought to be. Okay, this isn't a very interesting example because it's something we could do using, you know, our algebra skills. It's a limit we learned how to take actually using calculus and calculus 1, but I need an example where you use L'Hopital's rule multiple times, and this is going to do that for me. The limit of a rational function as x goes to infinity. So this is indeterminate. I'm not sure how obvious that is. I mean, here, infinity squared plus infinity minus 1, that's presumably pretty clearly infinity, but here we have infinity minus infinity. And I'm using the fact that I know what cubics look like. I know that that cubic polynomial looks something like this. So as x goes to infinity, this is growing to infinity as well. So this is indeterminate. It's infinity over infinity. Not forget to write the limit that time. And we'll hit this with L'Hopital's 4x plus 1 over 12x squared minus 2. And here, what I was expecting to happen in that last problem, this is still infinity over infinity. This is still indeterminate. 4 times infinity is infinity. 12 times infinity squared is infinity. But if we're trying to take an indeterminate limit, we have a tool for that now. We can hit this with L'Hopital's rule. The derivative of 4x is 4. The bottom (24x). And this is no longer indeterminate. A finite number over infinity is 0. So here we could just use L'Hopital's rule repeatedly and it all worked out. There's no guarantee that that will happen. Let me see if I can just off the top. Or if we use L'Hopital's rule and it does work, that's fine too. We'll attack this problem using L'Hopital's rule, and whatever happens, happens. So E, the exponential, grows really fast. E to a big number is big. E to infinity is infinity. That's hopefully intuitive. Then E to the negative infinity. See how well you remember your graphs. Here's so infinity over infinity. This is indeterminate. The derivative of e to the negative x is negative e to x. Is I guess I got copy. This is a perfectly clean application of happy. I mean, 0 over infinity. This is 0. This is 1. Let me sure it's trying to divided by e to the x. My instincts were perfect. So what have I done here? I've screwed up somehow. So we're going to infinity. The derivative of e to the, what am I doing? Why did I say this is 0 over e to the x? I just, usually when I make a mistake, I know what I'm doing, but this was just inscrutable. So we took the derivative, you know, this is now infinity minus 0. We're still going to infinity. So this is infinity minus 0 over infinity. So this is still indeterminate. And we can use L'Hopital's rule again. All right, I was right. I thought this was going to be a situation where L'Hopital's rule fails, and it is a situation where L'Hopital's rule fails. No idea what that error was about on my part, but as we keep taking derivatives, this is just going to flip-flop between e to the x minus e to the negative x will become e to the x plus e to the negative x will become e to the x minus e to the negative x. It will just keep flopping between those. The denominator doesn't change. And we keep getting the same indeterminate form. We keep getting infinity over infinity. So this limit exists, but L'Hopital's rule isn't a tool that lets us find it. We should also be careful, something like the limit as x approaches infinity of the sine of x divided by x squared. We can't just sort of bug infinity in because, I've been saying informally things like infinity squared is infinity, but the sine of x, as x gets big, the sine of x is bouncing up and down. It's oscillating. So the top does not exist, but it's not going to infinity, so we cannot use L'Hopital's rule here. And again, there are ways we could approach this. We could approach this using the squeeze theorem, if you remember that. We could maybe just intuit the answer. That top isn't going anywhere, but it's stuck between -1 and 1. The top is always going to be small, and this bottom is getting bigger and bigger. So something small over something that's going to infinity. This limit is going to be 0, but we didn't get that using L'Hopital's rule. We just kind of thought it out. L'Hopital's rule has a few other applications. You can occasionally use it for products. I don't know if I want to talk about that. I'll look at what we're covering this week and make a decision, but whether it's that or something else, looks like the end of class, and I will see you at 8 a.m. tomorrow.